Okay, we're going to look at the last 3 problems for the notes on 4.1, 4.2. Okay, question number 8. The graph of the derivative of a function is given. Find where the function is concave up and where it is concave down and where it has points of inflection. Okay, so this is, again, the first derivative. All right, and the first derivative tells us increasing and decreasing information. The second derivative will tell us concave up and concave down information. So what I need to look for on my first derivative is where the first derivative is going to have slopes of 0. So I'm just going to kind of indicate that. It looks like the second derivative will have 0 slopes at -0.5 and +3. Okay? So these are the locations where f double prime is equal to 0. Okay, so the second derivative tells us, the first derivative slope tells us the sign of the second derivative. So the slope of the first derivative on the interval from -∞ to -0.5 is a positive slope, all right, which means that my function is concave up. The slope of the first derivative is negative between -0.5 and +3. Okay, that means my function is concave down. The slope of the first derivative is positive from 3 to infinity, and so my function is concave up. We could also graph, roughly the second derivative, and I don't know exactly what it's going to look like, but I do know it's going to be a quadratic. So this is the second derivative estimate for the graph. Okay, and again, we see it's positive to the left of -0.5, positive to the right of 3, and negative in between. Okay, so we can answer the question. Find where the function is concave up and where it is concave down. So we'll say f is concave up on the intervals from -∞ to -1/2 and from 3 to infinity, because we could say f double prime is positive. Okay. And f is concave down on the intervals from -1/2 to 3, because f double prime is negative on that interval. Okay, so the inflection points, let me go back. Inflection points would be -1/2, f of -1/2, and 3, f of 3. So inflection points occur at -0.5 and +3 because, why do they occur? Because f double prime changes sign from positive to negative and negative to positive. So I'm going to say positive to negative at x equals -0.5 and negative to positive at x equals 3. Okay. Next question, number 9. Using a calculator, find the values of x at which x squared e to the x changes concavity. Okay. So let's take a look. I think I can actually do most of this without a calculator, But if I want to know estimates for what the values are, then I'll need to use my calculator. But let's take a look. So changing concavity means we need to look at our second derivative. In order to do that, we first have to look at our first derivative. So the first derivative of x squared e to the x, we're going to have to use the product rule. Okay, so x squared times e to the x plus 2x times e to the x. I like these kinds of questions because they're factorable. Pull out an x e to the x, we're left with an x plus 2. I would like to know, well, I don't need to find my critical points, but I could find it very easily from this form. So let's just do that for practice since we have a little bit of time. Critical points would be at x equals 0, because that would be 0. E to the x is never 0, so I don't have to worry about that. And x equals negative 2. So this graph potentially has maxes or mins at these 2 points. Okay, we technically don't need to find our critical points in increasing, decreasing information. So let's go to our second derivative. Now we can either take the second derivative from this first equation or from the second equation. I think it's probably easier just to take it from the first equation. Either way, we're going to have to do product rule. So second derivative will be, well, x squared e to the x, that's the same as what we had. So I'm going to get this same piece, x squared e to the x plus 2x e to the x. That's the derivative of the first term. Then I need to use the product rule on the second term. So that will be 2x e to the x plus 2 e to the x. So that's the second product rule for the second term. All right, can we simplify anything? Looks like we have a common or like terms. So f double prime of x is equal to x squared e to the x plus 4x e to the x plus 2 e to the x. All right, let's factor, pulling out a common factor of x squared. So we get x squared plus 4x plus 2. Okay, this does not factor nicely, but we could complete the square. So I'm going to do a completing the square on this one. So that's x squared plus 4x. That's the square I'm going to complete. So I'm going to need to add in a 4 and subtract a 4, so it remains balanced. All right, so this is x plus 2 squared minus 2. Okay, I'm only doing that here because I can't really illustrate using a calculator, but I can solve this for its zeros. So x plus 2 quantity squared is equal to 2, and x plus 2 is equal to positive or negative square root of 2. And so x is equal to negative 2 plus or minus the square root of 2. These are the locations of potential inflection points, as long as f double prime is changing sign. Okay, so let's take a look at a second derivative number line. So f double prime number line would have 2 points on it, negative 2 minus the square root of 2, and negative 2 plus the square root of 2. Those are the locations where the second derivative is 0. Okay, and this graph, x squared plus 2 minus 2, right, has a vertex at negative 2, negative 2, and it's opening up. So that would mean that the second derivative is positive, then negative, then positive on the number line. E to the x is always greater than 0. So I don't have to worry about that piece. So I know on my second derivative, The y values are positive, then negative, then positive. What does the second derivative tell me about my function? It tells me that my function is concave up, then concave down, then concave up. Okay, so that means that because f prime changes sign from, well, I could just say changes sign, okay? Because f prime changes sign at x equals -2 plus or minus root 2, we know that these two places are places of inflection, and that's where f changes concavity. So f double prime changes sign at these two places, so f of x changes concavity. All right, one more question. Oh, and two parts. Find the points of inflection in the following functions. Determine where the function is concave up or concave down. And no calculator. Okay. All right, first function is a cubic. So f prime of x, derivative, 3x squared minus 12x plus 12. Factorable, 3 times x, quantity x squared minus 4x plus 4. That's the same as 3 times x minus 2 squared. Okay, I need the second derivative, f double prime of x. I'll just use this form because it's pretty simple. So that's a 6x minus 2 to the first. Okay, where is this equal to 0? At x equals 2. Okay, thinking about the second derivative, this is a positive linear expression. So that means at 2, the second derivative is 0. To the left, it's negative. To the right, it's positive. So we're going to say f of x is concave up on 2 to infinity and concave down on negative infinity to 2. Okay, it's concave up because f double prime is greater than 0, and it's concave down because f double prime is less than 0. Okay. All right, let's take a look at the second question, part B. F prime of x is 2/3 x minus 1 to the negative 1/3. That's the same as 2 over 3 x minus 1 to the 1/3. Okay, this second derivative, I actually like this form better. So we're going to get negative 1/9 x minus 1 to the negative 4/3, or negative 1 over 9 x minus 1 to the 4/3. Okay. All right, so the second derivative equals 0, never. There are no places for x where the second derivative is 0. All right, but the second derivative is undefined when the denominator is 0. Okay, that happens when x minus 1 is equal to 0, so x is equal to 1. Okay, so we can't just assume, because we found a 0 of the second derivative, that there's a change in concavity happening. So take a look at your number line. Notice that the denominator is being raised to the 4th power, and then you're taking the cube root, or vice versa. Either way, raising something to the 4th power is going to make it positive no matter what. So the denominator of this derivative will always be positive for all x values, but the numerator is always negative, which means the second derivative is always less than 0. This graph is always concave down. Okay, if you recall, the graph of an x to the 2/3 function has a sharp point in it. Okay, that's why this graph has no change in concavity. All right, that's the end.